Okay, so welcome back. In this video, we're going to just do some general discussion about MOSFET performance. And we're going to look at things like thermals and power usage and, applying a square wave to the gate and see what happens, and just some general discussion to get a feel for the operation of a MOSFET. Now, what I'm going to do is I'm going to set up this circuit on my bench, and I'm going to use an IRF 510 MOSFET. And I'm going to apply a square wave, or using my function generator, and apply square wave. And then on the drain to source, the output, I'm going to apply a 10 ohm, 10 watt resistor with a DC supply around 10 volts. And just measure stuff and see what's the temperature of the case of this MOSFET, the temperature of this resistor. Just look at the power usage as you vary the duty cycle, just some general discussion. Now this is the MOSFET we're going to use. It's, like I say, IRF 510, power MOSFET, TO220, GDS. As you look from the front, you get gate, drain, source. It's an N-channel MOSFET, and I highlighted a few things we just need to keep in mind. Maximum, absolute maximum drain to source voltage, 100 volts, not a problem. My power supply only goes up to 30 volts. Gate to source voltage, maximum plus or minus 20 volts, not a problem. We're going to stay around the 5 volt range. Continuous drain current, this we need to be careful of. We don't want to go more than 4 to 5 amps. Pulsed, you can get a lot more. We're going to be having a pulse drain current, but we're just going to make sure we keep it below 4 or 5 amps just for safety. And the only other thing we need to look at is the gate to source threshold, which is basically the point at which you turn on the MOSFET so that you can have current flow in the output, the drain to source. And they're saying somewhere between 2 volts and 4 volts is required to turn this thing on. So that's about it. Again, we're going to be setting up this circuit on the bench and varying different things and seeing what we see. Okay, so here's my setup, and it might look a little bit confusing, but it's really pretty straightforward. It's the same diagram that I just showed, and down here is my MOSFET. So first of all, I am applying from this signal generator, function generator, I am applying a square wave, a variable duty cycle square wave coming out here and going between right here is the gate to source, which is gate to source. This yellow is the source. And I am applying the square wave there, and I have between the drain and ground, I have my 10 watt resistor, and that's this right here. I'm sorry, 100 watt, 10 ohm resistor. I'm also measuring the case temperature using this thermocouple on the resistor, and I'm feeding it over to here, to this multimeter. I am also measuring the voltage across this resistor, this load resistor, with this oscilloscope. On the oscilloscope, I'm measuring the gate to source voltage, basically the input square wave, and also I'm measuring the voltage across the load resistor. Okay? And that's these two traces. This is the input gate to source voltage, the square wave, and this is the output across this voltage across this resistor, which is 0 now because I've got my power supply off. And this is just basically my differential probe for my scope, which goes right here. So that's about it. I'm measuring temperature here. I'm measuring voltage in, voltage across this load. And I'm also measuring the case temperature of the MOSFET, which we're going to find out is really kind of irrelevant, but you can see I've got a thermocouple set right here. So what I'm going to do right now, here is the input gate source voltage. And I've got 3 volts with a 1.5 volt offset to make sure that it is at 0, okay? So it's going from 0 to 3 volts, and we said from the data sheet it should turn on around 3 volts. So we'll see if it turns on when we apply power, and this second trace is going to be the voltage across this. Okay, so first I'm going to turn on the thermocouple measurement for my resistor, and you can see I've got the power off. So what I'm going to do is I'm going to turn on the power for the power supply, and you can see it immediately jumps up to 10 volts across drain to source, including this resistor. And if you look over here, you can see the case temperature of the resistor, the 100-watt resistor, and you can also see that I'm getting an identical square wave on the output across this resistor, because they're right, 3 volts, this thing turns on. So it's on. I've got a 50% duty cycle, feeding 10 volts, 0.44 amps, and a little over almost 4.5 watts. Now, if we have 10 volts across this resistor, and it's a 10 ohm resistor, you might think, well, why don't I have 1 amp? Well, because of the duty cycle. The average is closer to half an amp, in this case 0.45 amps. So I have 0.44 amps flowing through the drain to source resistor output circuit, and you can see the temperature of the case of this is already up around 65, 66 degrees centigrade, okay? So what I can do is I can see if taking the offset down to, say, instead of 1.5 volts, I take it down to 1 volt, and bring the amplitude down to 2 volts, you can see the output shuts off because there's not enough gate to source voltage. So now what I'm going to do is I'm going to undo that and bring the offset back up to 1.5 and the amplitude up to 3, and now it's on. So what I can now do is I can see the effect of changing the duty cycle. So I can go on here. Right now I'm at 50% duty cycle, and I can set it to 40% duty cycle. Okay, so that's 40%. You can see the current has dropped to 0.35 and only 3.5 watts. And you can see the temperature's up at 84, still climbing. I can cut that down to 30% duty cycle. And you can see the input changes and the output matches exactly. I'm only feeding in 3 volts, this 3 volt pulse, and you can see I'm controlling 10 volts and 2.5 watts. So I can bring that down again to 20% duty cycle. You can see the current drop still 0.16 amps and 1.5 watts. And I can bring it down to 10% duty cycle, and there's almost no current flowing, and 0.7 watts. So that's the nice thing about pulse width modulation. You can see as I increase the duty cycle, I'm getting more and more current, more and more power. And what we can do is let's leave this at 50%, and we can watch this case temperature increase with, again, we've only got a little over 4 watts through this 100-watt resistor, and you can see the case temperature here is 94, 95 C. So we can look and see where it levels out, and you may be surprised. Okay, so here we are a few minutes later, and if you look over here, measuring the case temperature of our 100-watt resistor, again, it's 10 ohms, 100 watts, and it's only been 4.4 watts for the last 5 or 10 minutes, and you can see it's up near 128 degrees centigrade, and from what I've seen before, it kind of levels out at 130 centigrade. Now, if you look at my video I did recently on electronics thermals, you can see that is very, very hot. Not something you want to touch. and it's definitely something you're going to need cooling for. Again, this is a fairly hefty resistor, but if you touch this when it's 130 degrees, you're going to get a terrible burn. So just keep in mind that that is, you might not think there's a lot going on, but these things get very hot. So again, one of the great benefits of these MOSFETs is you can control power and voltage and current by varying duty cycle of a very low voltage, low current signal. You can control lots of power and lots of energy. And so that's one of the reasons why it's such a good thing. Now, just to mention, I am measuring the MOSFET temperature, and you can see it's only 28 C, so it's definitely not warming up at all. Again, it's only got, half an amp flowing through it.